Okay, are you ready?
Yes.
Okay, so this is Jinhyung Park from Pohang in Korea. I'm the host of the second part. So the first speaker of the second part is Jinhyung Park from Seoul. He will talk about Castelnuovo-Mumford regularity bound for threefold with the irrational singularities.
Okay. Thank you very much. Yeah, and thank you for giving me this opportunity. Today, I will talk about Castelnuovo-Mumford regularity bound for threefold with rational singularity. The outline of this talk is as follows. First, I review basic definition and properties of Castelnuovo-Mumford regularity. And then I will introduce the famous Heisenberg-Goto regularity conjecture. And I will also review some known results for this regularity conjecture. And then finally, I will show our main result. This is joint work with Wenbo from Arkansas. Okay, so today, throughout this talk, we always work over the field of complex number C. And let X be a projective variety embedded in some projective space PR, and let F be a coherent shape on X. Then by set-vanishing theorem, there is some integer M0 depending only on the coherent shape F, such that all higher cohomology of F twisted by OXM vanish. So it is natural to ask the following question. What is an explicit bound for this number M0? And the answer is given by the Castelnuovo-Mumford regularity. So let me give the definition. So we say that the coherent shape F is M regular with respect to the variant line bundle OX1 in the sense of Castelnuovo-Mumford. If this this higher cohomology vanish, then Mumford proved the following theorem. So if F is M regular, then F is M plus K regular for all non-negative integer K. So by this Mumford's theorem, the answer to this question is given by the Castelnuovo-Mumford regularity. And second one says that this F twisted by OX M plus K is globally generated, and this natural multiplication map is always surjective for all non-negative integer K. So we define the Castelnuovo-Mumford regularity of F is as follows. The regularity of F, denoted by this reg F, is the minimum of all integer among all integers such that F is M regular. Okay, so by Mumford's theorem, if F is, recall that F is M regular, then F is automatically M plus 1, M plus 2, and so on regular. So now we consider some special case. So in this case, X is PR, and let S be the homogeneous coordinate ring of PR. And then we can define this F using the coherent shape F and twisting by K and taking all its global section. Then this module F is in fact a finitely generated graded S module. Then it is well known that the highest degree of all minimal generator of piece CGG of F is less than equal to P plus regularity of F. So one may say that the Castelnuovo-Mumford regularity gives an upper bound for all CGG. So here is our setting for this talk. In this talk, we always denote X is an embedded non-degenerate projective variety. Here, this non-degenerate means X is not contained in any hyperplane in PR. So anyway, X is a non-degenerate projective variety, and with these three invariants, I will always denote N by the dimension of X, and E is always the codimension of X, and D is the degree of X. Then the Castelnuovo-Mumford regularity of this projective variety is defined by the regularity of ideal shift of X in PR. This is the definition of Castelnuovo-Mumford regularity of projective variety. Then by this fact, we immediately see that the highest degree of minimal generator of ideal, the homogeneous ideal of X, is less than equal to the regularity of X. So this means the Castelnuovo-Mumford regularity of variety give the upper bound for all defining equation. Okay, then let me introduce the Eisenberg-Goto regularity conjecture. Eisenberg-Goto conjectured that the regularity of any non-degenerate projective variety has regularity less than equal to degree minus codimension plus 1. This statement is the regularity conjecture. Then by considering this short exact sequence, we see that the regularity of X is less than equal to M if and only if X is M-1 normal and OX is M-1 regular. These two are equivalent to this following. So we say X is M-1 normal if and only if this natural restriction map is surjective. And we say OX, the structure shift OX is M-1 regular if and only if this all higher cohomology of the structure shift twisted by M-1 minus I vanish for all positive integer I. Then by this fact, we immediately see that the regularity conjecture is equivalent to proving the following two things. The first one, X is D minus E normal. And second one, the regularity of the structure shift is less than equal to degree minus codimension. So we may say that the second part, this second part is a part of the original regularity conjecture. And I will say that this is OX regularity conjecture. Okay, then here are some known results, some known positive results to regularity conjecture. So first one, every hypersurface and every complete intersection variety satisfy the regularity conjecture. Actually, this is very trivial fact. And the first non-trivial fact is maybe due to Castelnuovo. He proved the regularity conjecture for space smooth curve. So every smooth projective curve in P3 satisfied the regularity conjecture. And almost 100 years later of Castelnuovo's work, Grujong, Lazarsfeld, Peskin complete Castelnuovo's work in the sense that they proved that every projective curve satisfied the regularity conjecture. And shortly later, Pinkham and Lazarsfeld showed that every smooth projective surface satisfied the regularity conjecture. And shortly after, Gibran proved that every smooth projective threefold such that the projective space has dimension n is to 9 satisfy the regularity conjecture. And Shijong-Wak proved that the smooth threefold in codimension 2, so the projective space has dimension 5, satisfy the regularity conjecture. Okay, this is maybe all known result. And let me give one remark about this Grujong, Lazarsfeld, Peskin's result. Actually, they not only proved the regularity conjecture, but also they actually classify the extremer curve, namely Yeah, actually their result says that regularity of any non-degenerate projective curve less than equal to degree minus codimension plus 1. And they also prove that if the curve, they actually prove that the curve has maximal regularity if and only if C is the one of the following 4 cases. The first one is trivial case, C is plane curve. Second one is also trivial, C is rational or elliptic normal curve. And third one is also a little bit trivial, C is smooth rational curve with degree equal to codimension plus 2. Actually, this case is 1-point isomorphic projection from this second case. And finally, this last case is highly non-trivial result. Actually, C is a smooth rational curve with extremal secant line. It is easy to see that if C admits this extremal secant line, then C has maximal regularity. But the point is the converse. They show that if C has maximal regularity, then except trivial cases, C always smooth rational curve and admit extremal secant line. Okay, anyway, these are all known results. And next, we consider some general weaker result. So here we assume that X is a smooth projective variety embedded in some projective space, PR. Then in 1980, Mumford proved that the regularity of a smooth projective variety of dimension n is bounded by n plus 1 times d minus 2 plus 2. So one may think that this result says that regularity is bounded by dimension plus 1 times degree plus some constant independent of degree. Okay, actually, recall that the original regularity conjecture says this predict this very sharp bound, but some in weaker sense, this conjecture says that regularity is bounded by degree times 1. But Mumford result only says that if X is smooth, then regularity is bounded above by dimension plus 1 times degree. And in 90, and Noma's result is maybe almost 10 years ago. And this Bertram Ein Rajasfeld result appeared in maybe 90. And they slightly improved Mumford's result. So their result says that the regularity of the smooth projective variety X is bounded by codimension times degree plus some constant if codimension is smaller than the dimension. And if codimension is bigger, rather than dimension plus 1, then their result is essentially similar to Mumford's result. Dimension plus 1 times degree plus some constant. And recently, I and Shijong-kwak improved the previous result. We proved that regularity of smooth projective variety X is bounded above by dimension times degree. So our result is slightly degree. Our result is slightly better than these two previous results, because if codimension is smaller than the dimension, then this variety X should be very special. So in general case, the general result only says that dimension plus 1 times degree plus some constant, but our result says that dimension times degree plus some constant. Anyway, if dimension is smaller than 14, actually this bound is coming from Messer's work on projection. Anyway, if we assume the dimension of X is less than equal to 14, then we have almost a sharp result. Actually, Shijong-kwak proved that under this assumption, the smooth projective variety X is less F satisfy almost regularity conjecture up to some constant depending only on the dimension. So in special case, in threefold case, this constant can be taken 1, and if dimension is 4, then we can take 4. Okay, so the smooth projective threefold has regularity bound as degree minus codimension plus 2. Okay, but recently, McLaughlin and Piva constructed counterexamples, series of counterexamples to the Eisenberg-Otto regularity conjecture. Actually, they prove more. Their main theorem says the following. So for any polynomial theta x, there exists a non-degenerate projective variety x of degree t such that the regularity of the structure shape is bigger than equal to this polynomial of D in D. So recall that the regularity conjecture essentially says that we can, if we take the polynomial is equal to x, then the regularity of structure shape, this is a special case of regularity conjecture, the regularity of the structure shape should be less than equal to this polynomial, right? This should be D. But McLaughlin and Piva says that this is not true for certain non-degenerate projective variety. And moreover, we cannot take any, we cannot expect any polynomial bound for regularity for any projective variety. So anyway, this theorem immediately showed that the OX regularity conjecture is not true. So in particular, the regularity conjecture is also not true. But here is one important remark. All non-counterexample, actually all counterexample constructed by McLaughlin and Piva to the regularity conjecture are highly singular. In particular, all of their examples are non-normal variety. So it is natural to ask this following two questions, which are still open. So first one says that does the regularity conjecture hold for smooth projective variety? Yeah, for example, it is known that the OX regularity conjecture is true for smooth projective variety. I will explain this result later. Anyway, the second question is more general one, which mild singular varieties satisfy the regularity conjecture or OX regularity conjecture. Okay, then yeah, let me explain some result about OX regularity conjecture. Yeah, Noma and Sijongkwak and myself and Moraga, myself and Song prove this theorem. So let X be a non-degenerate normal projective Q-Gorenstein variety with isolated singularity. Then, so yeah, this case contains the smooth case. Anyway, under this assumption about some singularity assumption, we can prove the following three things. The first one, the regularity of the structure shape is always less than equal to degree minus codimension. So this first statement says that OX regularity conjecture hold for this variety, normal projective Q-Gorenstein variety with isolated singularity. So in particular, OX regularity conjecture hold for smooth projective variety. And second and third one, in these two items, we actually classify the extremer, and the next two extremer cases. So if the OX regularity is equal to degree minus codimension, if and only if X is a hypersurface or X is a linearly normal variety with degree is equal to codimension plus 1 or degree is equal to codimension plus 2. Actually, these two cases are well classified. Yeah, it is classical result due to Del Petro, Berrettini, and maybe Fujita. They actually classify linearly normal variety with these two degrees. And if regularity of OX is equal to degree minus codimension minus 1, if and only if X is an isomorphic projection of the second one, so this linearly normal variety with this degree, or X is a linearly normal variety with degree 1 higher, or a complete intersection of type 2, 3. And yeah, there are 3 ingredients to prove this theorem. The first one is Noma's study on positivity of double point divisor. This double point divisor is minus kx plus degree minus dimension minus codimension minus 1. Here this h is hyperplane section. And yeah, this double point divisor is nothing but the non-isomorphic locus of generic inner projection of X to some hypersurface. And Noma actually proved that this double point divisor has satisfied certain positivity condition, except some special cases. Actually, if X is smooth, then Noma's result implies that this double point divisor is semi-ample. So in this case, if in general case, this divisor is semi-ample, so we can apply Kodaira-Vanishing theorem to prove this first case, OX regularity conjecture. And one of the most difficult exceptional cases is scroll over some smooth projective curve. In this case, I and 시종과 used Castelnuovo's genus bound to prove OX regularity conjecture for scroll case. These 3 are essential ingredients for this OX regularity conjecture. Okay, so yeah, let me recall this question. It is very natural to ask which mildly singular variety satisfy the regularity conjecture or OX regularity conjecture. So it is natural to ask which singularities are mild one. Yeah. In this talk, we consider the singularity appearing in minimal model program or moduli theory or Hatch theory. So they are log terminal, log canonical, rational, or Dubois singularity. Recall that every log terminal singularity is log canonical, and every log terminal singularity is rational, and every log canonical or rational singularity is Dubois. Here recall the definition of Dubois singularity. This is very special. This is very technical definition. But if we know that the variety X has Dubois singularity, then this map is always surjective for all I. This is an important property of Dubois singularity. Okay, so we by Grudong, Lajaspelt, Peskin, we know that every projective curve satisfies the regularity conjecture. So the next case should be the surface case. So here are some results about regularity conjecture for mildly singular surfaces. So Wenbo-Niu proved that if S is a non-degenerate normal projective surface with rational or low canonical singularity, then this S satisfies the regularity conjecture. And Wenbo-Niu and I also checked the regularity conjecture for normal projective surface with Dubois singularity. Recall that this result contains this Niu's result because rational or low canonical singularity are all Dubois. Anyway, we proved this quite general result for mildly singular surface. And here is some open problem for regularity conjecture for surfaces. The first one should be, recall that Grudong, Lajaspelt, Peskin classify the extremal curve. And in previous case, in OX regularity conjecture case, we also completely classify the variety with extremal and next to extremal cases. So it is natural to ask to classify all normal projective surfaces with Dubois singularity, or classify all smooth projective surface such that the regularity is maximal. And second one, it is also natural. Does the regularity conjecture hold for any projective surface or any normal projective surface? Yeah, as far as I know, this problem is also widely open. Okay, so let me consider the threefold case. So yeah, the McLaughlin-Piba, they also constructed some counterexample with small invariant. Actually, yeah, they cannot construct surface counterexample, but they can construct threefold counterexample. One of their counterexample is a non-degenerate projective threefold in codimension 2, such that this X has degree 31 and regularity of X is 38. So in this case, this inequality shows that this threefold give a counterexample to the regularity conjecture. And yeah, we remark that this threefold has one-dimensional singular locus. Yeah, recall that in surface case, we assume the surface is normal. So in this case, surface has only isolated singularity. And here, this example says threefold has one, if threefold has one-dimensional singular locus, then there is counterexample. So one may expect that the size of singularity locus is an obstruction to the regularity conjecture. Okay, anyway, recall that Jinhyung proved these two theorems. So yeah, recall that if X is codimension 2 threefold, smooth threefold, then the regularity conjecture holds. And in general case, Jinhyung's result says that regularity has still very good bound. This is only one-off from the regularity conjecture. And our main result is a generalization of Jinhyung's result to threefold with mild singularity. So let X be a non-degenerate normal projective threefold in P E plus 3. So this X has codimension E. And if X has rational singularity, then we have the same bound to Quark's result, right? So the regularity of X is less than equal to degree minus codimension plus 2. And if X has Cohen-Macaulay-Dubois singularity, then the regularity of X is less than equal to degree minus codimension plus some number depending only on the codimension. And moreover, if X has Cohen-Macaulay-Dubois singularity and codimension is E, codimension E is equal to 2, then the regularity of X is less than equal to T minus 1. So this is sharp conjectural bound. Moreover, we could classify the extremal case. If regularity of X is equal to T minus 1, if and only if X is a variety of minimal degree, so this means X has degree 3, or X is a complete intersection of type 2-2. Here, we note that in our cases, if X has rational or Dubois singularity, then X could have one-dimensional singular locus. Okay, so anyway, this codimension 2 case is particularly interesting because this McLaughlin-Piba's counterexample appear in codimension 2 case with one-dimensional singular locus. So this result may be, this codimension 2 result is maybe interesting. Okay, so now, in the remaining of this talk, I will prove this main theorem. Okay, so the main technique is projection method. This method essentially due to Castelnuovo. Recall that Castelnuovo proved the regularity conjecture for space smooth curve. So yeah, let me briefly review Castelnuovo's argument. Actually, yeah, in this argument contains some cohomological method, and this is Cipiro's interpretation of Castelnuovo's original argument. So anyway, C is a smooth space curve in P3. Then we take a general projection of C to plane curve. Okay, then the classical trisecant lemma says that the length of any fiber of this general projection has, yeah, length of any fiber is n most 2. This is the theorem, this is the trisecant lemma. Then by this fact, the length of any fiber is less than equal to 2. So we have this surjection from here to this push port. Then one can easily check each corner is this shape. The push port of this, actually this is minus double point divisor of this outer projection. Anyway, then from this short exact sequence, we have this surjection. Surjection. Actually, this is kind of Kodaira anything for here, H1 for this shape. So we have this surjection, and there is natural surjection from here and natural injection from this one to P3. So yeah, this map are all surjective. So we see that this one should be surjective, right? From here to here. This means C is D minus 2 normal. So yeah, actually the OC regularity part is easy. Actually, it immediately follows from Castelnuovo's genus bound. So this essentially proves the regularity conjecture for smooth space curve. So yeah, we want to generalize this projection method to higher dimensional case. So let X be a non-degenerate Cohen-Macaulay projective variety. Yeah, here this Cohen-Macaulay assumption is necessary. Anyway, and then take a general projection to hypersurface as before. So pi is a general outer projection of X to X bar in Pm plus 1. Then let this one is center of projection. So this is general E minus 2. Here this small e is the codimension of X. Codimension of X minus 2-dimensional general linear subspace of PR. Then we can consider the fiber of projection. Yeah, since we assume this is general, this is always a finite scheme in some projective space. This space is spanned by X and this lambda. Okay, so this is a finite projective scheme in some projective space. But unfortunately, yeah, this natural map is not surjective in general in higher dimensional case. Moreover, if this is surjective, the kernel is very complicated. So we cannot generalize Castelnuovo's argument to higher dimensional case in this naive way. But instead, Raja's part slightly modified the Castelnuovo's original argument as follows. So here this V is the all linear form on the all linear form defined on the center of a projection, and we take some symmetric power of this vector space V and take some linear subspace Vj such that V1 should be V itself, and V2 should be the second symmetric product of V. Then there is a natural map WK. WK is this natural map. Okay, so this is kind of modification of this map. Then the fact is the following. If every fiber of general projection is k+1 regular, then we can find vector spaces V1 to Vk such that the Wk is surjective. So yeah, actually, yeah, in Castelnuovo's original argument, we directly take the map from here to the push forward of OC instead of this one. Then, yeah, and in this argument, the surjectivity of this shape to this one is very essential, very important. So it is also very important, crucial to show the surjectivity of this map WK. And this is essentially to equivalent to prove the every fiber of general projection is k+1 regular. So anyway, we assume WK is surjective, then the corner of WK is vector bundle because we assume X is Cohen-Macaulay. Then we have this short exact sequence, and then we can take the dual of this short exact sequence as follow. Then here, yeah, here the regularity, if we can control the regularity of E, then we can control the surjectivity of this map, the surjectivity of global sections on this map, and all higher twisted, all higher cohomology of twisted of this structure shape. So it is essential to control the regularity of E. And yeah, it is almost equivalent to control the regularity of each dual. And here, yeah, these are all OPM +1 and some twisting. So the vanishing of this part is easy. So the remaining is the vanishing of this part. So here we assume X satisfies the Kodaira vanishing because this shape consists of the dualizing shape. So this is why we need to assume X as mild singularity. So if X has rational or Cohen-Macaulay-Dubois singularity, then X satisfies the Kodaira vanishing theorem. So anyway, then if we assume Kodaira vanishing, then this short exact from this short exact sequence, we can see that this dual of E, sorry, this K, yeah, this is E star. E star is -2 regular. Then since E is equal to some wedge power and some twisting, so it immediately follows that the regularity of E is bounded over by degree minus codimension +1. This is conjectured bound for, yeah, in Eisenberg-Goto regularity conjecture, and plus some constant. And yeah, this gives also an upper bound for regularity of X. So the problem is to take Vj as small as possible such that Wk is surjective. Okay, anyway, this proof, the proof of under this surjectivity assumption and Kodaira vanishing assumption, the regularity of X is bounded by this one. This proof is essentially due to Lorentz sign. Okay, so yeah, in our case, in our threefold case, we have to take, we first have to show the smaller regularity bound for projection. Then, yeah, this essentially gives the regularity bound of threefold. So let me consider in detail the fiber of projection of threefold. So let X be a non-degenerate normal projective threefold in PE+3 and take a general projection as before, and let XY be a general, not general, XY is any fiber, arbitrary fiber of this general projection. Then the main theorem essentially follows from this main technical theorem. So here we assume X as rational singularity. then every fiber is 4 regular. And if X has Cohen-Macaulay-Dubois singularity, then every fiber is 5 regular. And moreover, there are only finitely many points Y in hypersurface such that the fiber is not 3 regular. So this means almost all fiber is actually 3 regular, and only finitely many fiber has exactly 4 regular. Yeah, in this exceptional case, so XY is not 3 regular, then XY is decomposed as 2 parts, G and Q. Here this G is a finite scheme with regularity 3, and Q is supported in the smooth locus of X, and it is reduced point in the fiber. Okay, so yeah, this theorem essentially gives some classification of general fiber of general projection of threefold. And yeah, so if we assume X has rational singularity, then this theorem immediately implies that W3 is surjective. And in this case, we can take V3, one-dimensional V3. And if X has Cohen-Macaulay-Dubois singularity, then W4 is surjective. And we can take V3 and V4 as follows with these two properties. So this number, 1 or this one and this one, give the bound in our main theorem as follow. Those number give this number. Okay, so yeah, let me explain how to prove this theorem. So there are 2 cases. Yeah, recall that XY is a fiber of general projection. So there are only 2 cases. XY does not meet the singular locus of X, or XY meet the singular locus of X. So the first case, we assume X does not meet the singular locus of X. So the support of XY is contained in the smooth locus of X. Then by dimension counting argument, we can show that, yeah, here this Tx, here this one means projective tangent space of X at the point X. Okay, then the intersection of projective tangent space with the center of projection, lambda, then their dimension is less than equal to 0. This is easy dimension counting. Then this implies this one, the linear span of X and the center of projection with this projective tangent space has at most dimension 1. So this is equivalent to saying that the fiber is curvilinear. This means this fiber can be embedded in some curve. Then once we prove the fiber is curvilinear, then we can apply Gibran's dimension plus 2 secant lemma. This is on a generalization of classical tri-secant lemma. So this dimension plus 2 secant lemma and some dimension counting argument implies that the length of fiber in this case 1 has at most 4. So this inequality for length immediately implies the result. The regularity of fiber is less than or equal to 4, and this is 4 if and only if XY consists of distinct 4 collinear points, and there are only finitely many 4 collinear point fiber. Okay, so yeah, if the fiber does not meet the singular locus, then it is easy to control the regularity of a fiber. So actually the difficult case is this second case. The support of X meet the singular locus. For this case, the essential ingredient to deal with this case is this following theorem. Yeah, this technical theorem essentially proves some upper bound of the dimension of some special secant variety. So let X be a project variety and delta be the codimension of a singular locus. Then we consider all line with these two technical condition. Then the dimension of these secant line has at most dimension plus 1. Okay, then yeah, this technical theorem and some dimension counting argument implies that the fiber is supported at one point in singular locus. Actually, almost all fiber is supported at one point in singular locus, except finitely many exceptional cases, and over which exceptional point, the fiber has two parts. The first one, actually the fiber has two support. So that this statement says that the fiber, if a fiber meets singular locus, then the fiber has one support or finite or two support. In two support case, there are only finitely many. And in this case, the Q is supported at smooth locus and reduced point. And the support of G is in the singular locus. Okay, so this is the important consequence of this theorem. Then in this case, the regularity of this fiber is equal to regularity of G plus regularity of this Q. This is 1. So the regularity of G is bounded by the length of G, but unfortunately, length G can be very large. So this considering length is not useful in our case. So instead, considering length, we consider Lowell length. So let A be a local artenian ring. Then Lowell length of A is defined as follows: the maximal integer I such that m i's power is not 0. This is the definition of Lowell length. Then Wenbo Niu proved that if G is a finite projective scheme supported at finitely many points, then the regularity of G is less than equal to the Lowell length of the local ring of this finite scheme. So yeah, let me consider our geometric case. So let X be a projective variety with positive dimension and P is a point. Then we can consider the local ring. But in this case, this local ring is not artenian. But we can consider the minimal reduction of this maximal ideal. And actually, we can take some linear subspace, because in projective case, the fiber is intersection of the point with some linear subspace. And if this linear subspace give a reduction of maximal ideal, and with this, if the minimal reduction has this property, and if we take some linear subspace give reduction of maximal ideal, then we can control the Lowell length. Actually, this is zero dimensional. Yeah, this is zero dimensional. So this is artenian ring, and the Lowell length is less than equal to this n-1. This n-1 is given by the minimal reduction. So go back to our case. So X is a non-degenerate normal projective threefold. Yeah, remark that here, this case, in these two cases, we don't assume X as mildly singularity. We only assume X as normal singularity, right? Then we have this conclusion, but finally we need this singularity assumption, because we need to apply this Bullion-Skoda type theorem. So here, if X has rational singularity, then, and let J be the minimal reduction of this maximal ideal, then this theorem says that MQ is contained in J. Here, this condition. So we can take M as 3. So then the Lowell length is bounded by 2 in this case. And if X has Cohen-Macaulay-Dubois singularity, then we can take 4. So yeah, recall that if the support of fiber means singular locus, then the fiber has 1 support or 2 support. And yeah, in any case, if X has a rational singularity, then Lowell length is less than or equal to 2. So the regularity of G is less than or equal to 3. And if X has Cohen-Macaulay-Dubois singularity, then Lowell length is less than or equal to 3. So regularity is less than or equal to 4. And yeah, this completes the proof of technical theorem about fiber of projection. So this implies the main theorem of 1 and 2. So finally, we consider the codimension 2 case. So if X has codimension 2 and non-degenerate normal projective threefold with Cohen-Macaulay-Dubois singularity, then we can take W4 as follow. Then in this case, we can show that the dual, in general case, dual of this corner is -2 regular. But in this case, we can show that the dual of E has -3 regular. Actually, this is equivalent to this 3 condition. And these first 2 conditions are theorem of Severi and Fulton-Rajasfeld. Essentially, yeah, these first 2 conditions follow from classical theorem about Severi and some result of Fulton and Rajasfeld. So the problem is this third case. So we only have to consider this third case. This means X is contained in some quadric hypersurface. Then if X is complete intersection, then the regularity is T minus less than or equal to T minus 1. Recall that if these 3 conditions hold, then regularity is T minus 2. And yeah, in this case, regularity of X is T minus 1. And we can also classify the equality case. And if X is not complete intersection, then using Shijong-Bak's result, we have regularity, we have exact regularity, exact regularity value. So we can also prove the bound, and we can classify we can characterize the equality case. This finish the proof. Okay, so I stop here. Thank you very much.
So any questions? Okay, I have a question. So when you define the regularity, so the ambient space is the project space, right?
Yes. Yes.
Can you generalize to the ambient, to the case when the ambient space is the weighted project space? So
yes, yeah, maybe, yeah, if yeah, we can still define the similar notion, but yeah, I don't know whether there is some result about the embedding in weighted projective space. Yeah, I don't know.
So there is no problem to define the regularity in the for the this weighted project space.
Yeah, I think so. So yeah, in weighted projective case, we can still take the minimal resolution of the ring. Then we can define regularity. Yes. Yeah, actually, yeah, you know, maybe this Popper and Paresky define some regularity, similar notion for abelian variety, right? And there is also multigraded regularity. There are some various notions if we consider another ambient space. but I don't know. There is some similar result about the bound for regularity. I don't know.
Okay.
Okay.
All right. Any other question? Okay, so if not, then rest. Thanks, speaker. Thank you.
Thank you.
Okay, how do I?
Hello, can you hear me?
Here. Okay.
Uh,
Okay.
uh,
So you're gonna share the screen, or right?
let me see.
Oh, wait.